In section 5.6, we take a look at partial fraction decomposition. So in this extra problem, we first give it an eyeball and verify that the degree of the bottom polynomial is greater than the degree of the top polynomial, right? In this case, it's all good. If the top polynomial in green had a degree that was equal to or greater than the bottom, we would have to do a little bit of long division before we even start. So notice that this problem can be written as 3x plus 2 on the top, and the bottom is a nice convenient polynomial that can be factored out. And whenever you have the denominator being a product of distinct linear terms like this, we're in business, we can use partial fraction decomposition. So the goal is to take that 3x plus 2, x minus 3, x plus 2, and break it up into pieces. How many pieces? Well, because you have two factors, you want to break it up into two pieces. The first piece will have an x minus 3, the second will have an x plus 2. And your job is to figure out the constants that will go up here so that this side is equal to that side. When considering taking the antiderivative of this, it's going to be equal to the antiderivative of that, and these two antiderivatives are a piece of cake to compute. So we're going to multiply both sides by the LCD. So multiply by the LCD, in this case, of x minus 3, x plus 2. And you can imagine that you're putting gigantic parentheses on both sides here and multiplying x minus 3, x plus 2, x minus 3, x plus 2. The left-hand side is a piece of cake. These guys cancel out completely, leaving you behind with 3x plus 2. For the right-hand side, be careful. You're going to do a product at a time. So when you multiply these two guys together, the x minus 3's cancel out, leaving behind a with a x plus 2. And then when you multiply these two guys together, you see that the x plus 2's cancel out, leaving behind a b times an x minus 3. We can write the left-hand side exactly as it was, and for the right-hand side, I see that if I were to FOIL everything out, I would be left over with a first-degree polynomial with some constant times x plus some constants. Instead of FOILing every single thing out, painstakingly collecting all of those terms and adding those like terms, I'm going to eyeball them and see how I can collect them efficiently. From this first product, I know I have ax involved, and I'm going to account for that by putting an a there. For that second product, I know I have a bx involved, and I'm going to account for that guy by putting a b there. So you get your ax, you get your bx. I can do the same thing for the constants. I'll have 2a for this guy and negative 3b for that guy. We're going to take the polynomial on the left and equate it to the polynomial on the right. That means that whatever coefficient the x had over here is going to be the same as the coefficient that the x had over here. So I have that a plus b is equal to 3. Similarly, whatever constant this guy had over here is equal to whatever constant that guy had over there. So I have that 2a minus 3b is equal to 2. So what we have in front of us is a system of equations. It's really like the old school systems of equations that you saw in your Algebra 1 or 2 classes, where you're asking yourself, when are these two lines intersecting? You can deal with this system of equations 1,000 different ways: substitution, elimination, or you can call on Desmos and put this into a matrix calculator, like how we done earlier, and you can solve it that way. So if you're going the matrix route, again, you would put 1, 1, 2, negative 3, 3, 2, and do a little bit of row reduction on that matrix. On the side here, I'm computing out the answer to this, and I get the matrix 1, 0, 11, 5, 0, 1, 4 over 5, meaning that the value of A is 11 over 5, and the value of B is 4 over 5. So let me go up just a second and copy and paste a little something from here. So our job was to find the integral of this function, and that's going to be equal to the integral of that function. But now we know the value of A is 11 over 5, and the value of B is 4 over 5. Right? So having these constants, we can then take the antiderivative of these functions easily. First of all, that 11 over 5 is just a constant. I'm going to take it, copy, paste it, nothing to do there. And I'm going to look at the antiderivative of 1 over x minus 3, which is the natural log of absolute value x minus 3. The next term, you have a 4/5 there, natural log absolute value x plus 2. Add the plus c because it's an indefinite integral, and we are all set.